Hello everyone, I'm Flavio Ascari, and I would like to present the work I did together with Roberto Bruni, Roberta Gori, and Francesco Logozzo. In title, Revealing Sources of Memory Errors via Backward Analysis. So we make two main contributions in our paper. One is more conceptual, is the first one, that is Sufficient Incorrectness Logic, that is a proof system tailored for backward inference of the sources of errors. And the second one, that is the more technical contribution, is Separation Sufficient Incorrectness Logic, that is a version of Sufficient Incorrectness Logic mixed with separation logic to handle memory allocations and programs with heaps. So the first contribution, Sufficient Incorrectness Logic, there are like a lot of program logics in the literature that are good at, very good at some specific tasks, but we started with this question, that is, identifying initial states that are useful for debugging. So consider this simple program where y is some variable that comes from the, let's say, the environment somewhere in the program before that. Here we get some x from the user, so an input. And depending on some condition on x and y, we set z to 42, that is the error. So the condition we are aiming for is to understand that the, let's say, a precondition responsible for the error is that y is odd. Of course, we would also like to have something on x, but we can't because x is an input of the user. So the best we can say is a condition on y, and we want to understand that if y is odd, then we always have like a possible execution where the user inputs an even number that will lead to the error. So to this goal, we started considering some known program logics from the literature. We started with OR logic, very well known, and incorrectness logic. That is a logic for under-approximation aimed at finding bugs, so it seemed a good fit. But for both of them, we found that they have some issues, because you can see here that if we want to identify the errors z equal 42, we get some preconditions that are not really what we're looking for, because one is false and the other is true. There is sort of an indication of the error in the post-condition of incorrectness logic, that odd of y appears there, but is not such a general thing that we can rely on that. So since our goal was starting from the error, so this z equal 42 in the post-condition, and we wanted to find the corresponding precondition, we thought, OK, maybe the issue is that both OR logic and incorrectness logic are based on the forward semantics. So they kind of follow the program forward where we want to go in a backward direction. So we considered instead a backward program logic in the literature that is necessary preconditions. And it has some better properties because of its backward nature, but it still doesn't capture the property we're looking for, because for technical reasons, for necessary condition, we want to consider the set of good states, so z different than 42, but still you can see that the precondition is true, so it's not highlighting the thing that we are interested in. And so, as you probably may guess from the schema on the right, what we turned our attention to was the backward under-approximation condition. And as you can see here, the bottom line, when we start from z equal 42, we are guaranteed to find the fact that y is odd, or let's say a subset of it. And so this backward under-approximation condition was exactly the thing that we were looking for this specific task of identifying initial states for debugging. Also, you see that I'm calling it backward under-approximation condition, but on the slide you see the SIL name. The point is that the backward under-approximation condition is not our contribution, but sufficient incorrectness logic are. I will get back to this point in the next slide. So for now, let me just try to give you some more evidence of the fact that this condition is useful. So the idea is that, why are we interested in this condition? I think the example already showed the idea, but the point is that in a SIL triple, if all states in the postcondition Q are errors, then from any state in the precondition P, there begins an execution. That there may be executions leading to good states if, for instance, the user inputs a particular value, but there is also a value that the user can input that will lead for sure to an error in Q. And so the precondition found by SIL is useful to pair together with Q to give input states that are evidence for this error that can be used for starting the debugging process. Another example of usefulness is the concept of manifest errors. The manifest errors were introduced by Lee et al. in the concept of incorrectness logic. They were manifest errors are errors that happens regardless of the context, and they were tested experimentally in the sense that they reported errors to the programmers, and the programmers usually fixed the manifest errors, while they usually didn't fix errors that were not manifest. So these are actually a practically relevant concept. And in the context of incorrectness logic, you need to check separately after finding the error if it is manifest or not. But with sufficient incorrectness logic, you can prove this already within the logic itself, just checking that this triple is valid where the precondition is true. So, as I said, the condition of backward under-approximation, that is the validity condition of SIL triples, was already proposed in the literature. Our new contribution in this sense is the proof system. What we gave was the first proof system for this backward under-approximation condition that is tailored for a backward inference. So starting from any post-condition Q, the proof system guides you towards the initial states corresponding to that post-condition, and also the comparison that I showed you very briefly before with other logics. As I said, this is the first contribution of our paper, that is the more conceptual one, but we also have the more technical part, that is the separation SIL. That is, as you may expect from the name, a combination of separation logic and sufficient incorrectness logic. And I mean, there are a lot of technical details, and you can find all of them in the paper, but here I will just go through an example, plus some remarks later. So consider this program. In this program, you have V is a standard C++ standard vector library. And what we are doing here is we use X to take a reference to the underlying buffer to the vector. Then we do a pushback, so we add an element to the vector B, and then we dereference this X reference that we got before. But the issue is that the pushback may reallocate the underlying buffer to the vector if there is not room to account for the new element. And if this happens, then the pointer X becomes invalid. As you can see, in separation SIL, if in separation SIL we want to capture this error, we start from the post condition that says exactly that X is deallocated, that is the error that we have, and separately true, and that means we don't care about the rest of the heap, because knowing the fact that X is deallocated is the only thing we care for the description of the error. And then using the proof system, we go backward through the program and we find the precondition. Basically, this first part here says that V is just a valid vector. And separately true, again, means that we don't care about what else is in the heap. We only care that V is a valid vector. And the very strong guarantee that we get from this triple is that from any state satisfying the precondition, so from any state where V is a valid vector and whatever is the rest of the heap, then there is an execution that reaches the error. That is exactly the case when the pushback decides to reallocate the buffer. If we, for instance, compare this with the incorrectness separation logic triple, we see that because of different goals, the incorrectness separation logic triples is a lot more precise on the post condition. It says that there is the error where X is deallocated, but it also has to specify a lot more about the shape of the heap there. And also the precondition, you again see the error, but this is not always the case because separation logic allows for weakening of the precondition or strengthening of the post. That is basically the same thing. And so in principle, you may find here more states than the ones that actually lead to the error. So in principle, a tool based only on incorrectness separation logic may have more states in the precondition that do not lead to the error. So just a bit of technicalities, but a thing that I really want to mention about about separation SIL is that is this theorem. So one very important thing that I forgot to mention is that P and Q in separation SIL are assertions. So they are syntactic object in assertions in a certain language, so something that you can manipulate programmatically. And the theorem says that for any syntactic assertion Q and any atomic command C, atomic commands are basic statements such as assignments, dereferences, allocation, and so on. Then there is another syntactic assertion P that is exactly the backrow semantics, so let's say the strongest SIL precondition for this assertion Q. So the assertion P is a syntactic one. And we can prove this triple. And the proof is very interesting because it's not just there exists one, but it gives you an algorithm to compute exactly this precondition, this assertion P. So on the one hand, the theorem is the basis of our relative completeness result, where we extend this from atomic commands to any kind of command by composing them. But it's also, the proof is a basic of, let's say, more practical applications, where, because we implemented this algorithm in a proof of concept implementation, it was part of a student project, and this validates our intuition that we can do backward inference using separation SIL. So, to conclude, there are, in the literature, many approaches to program correctness and incorrectness. We sorted and compared some of them, and we designed the sufficient incorrectness logic proof system as a sound and complete system, proof system for backward inference. And we provided an automated, or at least automatable, proof system for backward inference in the case of memory errors based on separation logic. As future works, we would like to extend the schema by including other logics, so to compare this more complex logic with the basic one that I showed you. And also, one future work that we actually did was the idea to follow incorrectness logic derivation backwards with SIL, and this is a work that I'm happy to say that has been conditionally accepted at OOPSLA 26. That's all from me. Thank you for your attention, and please feel free to ask any question.
Questions? All right. So super interesting talk. Thanks for it. So I guess I got a little bit sort of lost in terms of exactly the precision difference that you were talking about between the incorrectness separation logic and yours.
Okay, so very briefly, what can happen in general is that while you go forward with analysis in incorrectness separation logic, you may, the postcondition may grow bigger because of different code paths that leads to disjuncts. And if you reach some limit of disjunct, you may have too many to keep track of programmatically, so you want to drop some of them. And if you do, like some of the states in the precondition that led to those disjuncts in the post now don't lead to any error that you have still left in the post because you dropped the only disjunct that they were reaching. This is the kind of issue that you incur into if you do an incorrectness logic kind of analysis, let's say in a more practical setting. Instead, separation SIL does the opposite. It guarantees that all states in the pre will reach some states in the post, but of course, while going backward, you may need to drop some disjuncts, so some states in the post may end up not being reachable. So okay. You have this kind of duality in where you have the imprecision.
Right. Oh, super interesting. I'd love to talk further. You want to set up? Yeah.